Now, let me introduce the second part, the mode of radioactive decay. Radionuclides are unstable. In process of achieving stability, a part of nucleus of radionuclide disintegrates and emits particles and energy. It does this until it reaches stable state and is no longer radioactive. This photo shows us the periodic table of elements. As you've seen in this table, radioactivity is characteristic of elements with large atomic number. Elements with at least one stable isotope are shown in light blue. Green shows elements whose most stable isotope. Yellow and orange are progressively less stable. Red and purple shows highly and extremely radioactive elements. The nuclide has two big classes. The one is the radioactive nuclide, and the other one is stable nuclide. The radioactive nuclide emits particles rays and be changed into another nuclide. This phenomenon is regarded as nuclear decay. Today, we will introduce 5 main modes of nuclear decay. The first one is alpha decay, and the second one is beta-minus decay. The third one is positron decay. The fourth is electron capture decay. And the last one is osmotic transition. Let's see the first, alpha decay. As shown in the photo, alpha decay is one type of radioactive decay in which an atomic nucleus emits an alpha particle and thereby transforms into an atom with a mass number decreases by 4 and the atom number decreases by 2. So, alpha decay occurs in a very heavy elements, usually with its mass number bigger than 209. They can become more stable by emitting an alpha particle. So remember that in alpha decay, atom number decreases by 2, atom mass decreases by 4. So let's see the characters of alpha particles. The alpha particles are made of 2 protons and 2 neutrons. Alpha particles have a charge of positive 2 and a mass of 4. Alpha particles are relatively slow and heavy. Alpha particles have a low penetrating power. You can just stop them with just a sheet of paper. Alpha particles ionize other atoms strongly. The second mode of radioactive decay we call the beta-minus decay. As for beta-minus decay, it is a type of radioactive decay in which a beta ray and an antineutrino are emitted from an atomic nucleus. Beta-minus decay occurs in very neutron-rich elements. The whole process can be looked at as one neutron changed to one proton. They can be more stable by emitting a beta particle. So remember that in beta-minus decay, atomic number increases by 1 and atomic mass is unchanged. So let's see the characters of beta-minus particle. Beta-minus particle have a charge of -1 and a mass same as an electron. Beta-minus particles are fast and light. Beta- particles have a medium penetrating power. They can be stopped by a sheet of aluminum or plastics. Beta- particles cause less ionization than alphas. The third mode of radioactive decay is the positron decay. Positron emission is a subtype of radioactive decay called beta decay, in which a proton inside a radionuclide is converted into a neutron, while releasing a positron and an electron neutrino. In positron decay, a positive charged beta particle is ejected from nucleus. Positron decay happened only in artificial nuclei. So let's see the characters of positron decay. The positron decay occurs in nuclei that are neutron poor. The minimum transition energy required for positron decay is 1.02 million electron volts. So remember that in positron decay, atomic mass is unchanged and the atomic number decreases by 1. It is worth noting that positive charged beta particle is unstable. It cannot be exist for a long time. Positron emission usually followed by the annihilation. Annihilation is a process that occurs when a subatomic particle collides with its respective antiparticle, then produce other particles, such as an electron collecting with a positron, then produced 2 photons. As shown in these photos, positron travels only 1 to 3 millimeters before annihilation. During annihilation process, positron meet with 1 electron, then emit 2 511 kilo-electron-volt photons simultaneously along line between detectors. The fourth mode of radioactive decay is electron capture decay. In unstable nuclei, where the maximum available transition energy is less than 1.02 million electron volt, decay of neutron-poor radionuclears is by electron capture. In electron capture, an electron from one of the orbit's shells is incorporated into the nucleus and then converting a proton into a neutron. So remember that in electron capture, atomic mass is unchanged and the atomic number decreases by 1. The neutron-poor radionucleus of an electrically neutron atom absorbs an inner atomic electron. Then there were 2 results. The first result that shows the lower left of this picture. You can see an outer electron replaces the missing electron. An X-ray equal in energy to the differences between the 2 electron shells is emitted. Another result showing on the lower right of this picture. In an Auger effect, the energy releases when the outer electron replaces the inner electron is transferred to an outer electron. The outer electron is ejected from an atom, leaving a positive ion. So the last mode of the radioactive decay we called osmotic transition. The transition from the metastable state to the ground state is a isomeric transition, because there is no charge in atomic number. This radioactive decay process involves emission of a gamma ray. The actual process can have two effects. The first one is a gamma ray, and the other one is the internal conversion electron. As for the gamma decay, most of the daughter nuclei after alpha or beta decay are in excited state, so they release their energies in gamma rays and then live there in ground state. This phenomenon is called gamma decay. In this process, a gamma photon is emitted. The inner transmission is above phenomenon, but no gamma photon emission. The energy was transferred to the electron outside the nucleus. The electron may become an free electron, leave the nucleus in a ground state, combined by X-rays generation. So remember that in isomeric transition, atomic number unchanged and atomic mass unchanged, and the energy state changed from the metastable state to the ground state. At last, let's make a short summary of penetrating ability about three main radioactivity decay. The first, alpha particles have a relatively slow and heavy. Alpha particles have a low penetrating power. You can just stop them with just a sheet of paper. And as for beta minus particles, it are fast and light. Beta minus particles have a medium penetrating power. They are stopped by a sheet of aluminum or a plastics. And as for the gamma rays, it has a highest penetrating power. They are stopped by 3 feet of concrete or lead. So we can see that make this conclusion, alpha particles are easy to stop, and the gamma rays are hard to stop. Okay, that is all for this part. Thank you.